Howdy! I hope everybody's doing well. Welcome to another video reviewing your probability and statistics fundamentals. It's so great to be with you guys today on a Saturday morning. So today in this video, we're going to be shifting gears and talking about a topic that I find quite interesting. So as you may recall in the past couple of videos, we've been discussing the idea of sampling distributions and how we can take a lot of samples and plot the distribution of, say, the sample mean or the sample proportion. And using that distribution and the sample we collect, we can estimate with some degree of certainty the population mean or the population proportion. So while estimation is an important concept and it's used widely in the real world, one other thing we can do as a corollary to what we've been discussing is an idea called hypothesis testing. So I know this word might sound a little bit scary, but I'll try my best to distill it into easier terms. So, what is hypothesis testing in the first place? Hypothesis testing is simply a way to statistically verify a claim, right? So, I might make a claim, right? And you need a way to, see if my claim can be doubted, right? But you can't just say, oh, your claim is wrong because of such and such reasons, right? You can't just say, oh, I think your claim is wrong because of some baseless argument, right? We need a numerical way to, you know, test the validity of a claim, right? And this is where hypothesis testing comes into place. Hypothesis testing provides a framework for which to accept or reject claims that you see in the world. So I guess one way to motivate the topic of hypothesis testing is to think about something you guys all know in the real world. So I'm pretty sure you all have ordered a pizza at some point in your lifetime, right? And when you order a pizza, right? When you click the order button on, like, say, Domino's website, right? There's going to be some time that elapses, right? Between when you place the order for your pizza versus when you actually receive the pizza. So let's say I'm at my favorite pizza place, right? And the parlor claims that it takes 30 minutes to deliver a pizza, right? Now, I don't know, like, if this parlor's claim is right. And I can't just say, oh, your delivery time is slow because other places deliver faster, right? That's not really a good argument. So, what I want to do is think of a scientific approach in which I can, test the validity of the pizza parlor's claim, right? So, what I'll do is I'm going to collect a sample of delivery times, right? So, let's say these dots represent delivery times I've collected. So, you might have a data set of, like, one guy's order took 30 minutes, another guy's order took 15, 20 minutes, 25 minutes, 10, 35, 40, etc., right? So you collect this data, right, from sampling, customer deliveries, right? And we're not going to really talk about how we collect the sample. We're just going to say that we can collect the sample, right? And we get some data, right? So what we want to do is test, is the average delivery time, you know, of 30 minutes something viable, right? Does that sound like a sound claim by the pizza parlor, right? So this is the data I collect on delivery times done by the pizza parlor I'm studying, right? And I get its mean, right? So I'm going to call it X bar, right? Now, with this mean, right, I need a way of testing if I need a way of testing, is the mean that I get from my sample significantly different from the parlor's claim of 30 minutes, right? But the problem is my definition of significant versus your definition of significant can be different, right? So for example, if this sample mean was, let's say, 40 minutes, right? I might say that 40 minus 10 is, it's so 40 minus 30, right? Is not too bad, right? Only 10 minutes, right? But you might say that a 10-minute difference is really significant, right? And it's way too slow, right? Maybe 10 minutes is the difference between you ordering from that pizza parlor versus cooking at home, right? But another person could say, oh, 10 minutes delivery, I can wait 10 minutes longer. So that shouldn't be too bad. But the problem is, like, if we have a measurement where it's subjective, right? We don't have a concrete way or an objective way of verifying how significant a difference is, right? So what we want to do is statistically set some sort of threshold, right? Such that if I'm if I'm below a certain threshold, right, I'm going to say, okay, this difference is significant. Or when I'm above the threshold, I might say, oh, this difference is not too significant, right? The difference between my mean delivery time from when I sampled the parlor's data versus what the pizza parlor is claiming, right? So we need some sort of threshold, right, to say okay, if I'm above this threshold, then I'm going to say, oh, the parlor's claim like sounds reasonable, right? Versus, oh, the parlor's claim doesn't sound reasonable, and I have some evidence to back me up, basically. So we need some sort of threshold to do that. And this is where the term p-value comes in, right? So what do I mean by a p-value? So here's what I mean by a p-value, right? So imagine that we have the sampling distribution of mean delivery times, right? And here's my sample, right? This is the 40-minute mean, right? And we're assuming that at first the parlor's claim of 30 minutes seems reasonable, right? So we're going to have a distribution where the mean is 30, right? And we have a scenario, right, where we're getting a mean of 40, right? And we want to test, okay, if I'm getting sample whose mean delivery time is 40 minutes, right? What is the chance of getting something a little bit more extreme, right? So what is the chance that I can get a sample where the mean delivery time is above 40, right? What's the likelihood of me getting something that extreme, right? So we want to find this probability, right? And to find this probability, right, recall that we can use the z or t distribution depending on if the normality checks pass. And what we can do is we can get a z star or t star, and then we can look into t table and find what is this area right here, right? We can use the z table or the t table to do this. So by getting this probability and comparing against the threshold, we can see, okay, if I'm getting a sample observation where the probability of getting something more extreme is very less, then that signifies that this 40-minute delivery time on average is something very surprising, right? And it's not just due to random chance. This is something kind of rare, right? And we value things that are rare, like just like how we value rare diamonds, right, in the real world. We value extreme observations, right? Because if it's very unlikely that we can't get a sample whose mean delivery time is more than 40 minutes, it probably means that this sample has a statistically significant difference against the proposed 30-minute delivery time by the pizza parlor, right? And thus, we don't really have as much faith in that the pizza parlor's claim is true. So that's where we might want to reject it, right? So the intuition behind the p-value is we want to get this area in green to be as small as possible because that will signify that the sample we're getting is not due to random chance. It's not just from random noise. This sample actually might highlight something significant, and we want to capitalize on that. So that's why for p-value, we generally want this area to be lower. Now, note in this case, I'm talking about a one-tailed test. A two-tailed test would mean that you will also consider the area here as well, right? So you'll use the symmetry of the distribution and say if the total of this area plus this area like falls below the p-value, falls below our threshold. But we'll see more of that when we do the examples. I just want to build an intuition of what the p-value is and kind of why we're doing hypothesis testing in this way, right? So let's go through the examples and kind of make this more concrete, right? So in our example, let's actually continue our study of pizza parlors, right? So I like to order Domino's pizza. I have a favorite topping. You probably do as well. I like pineapples and jalapenos, but some people don't like that. A little bit off topic, but I like to order Domino's pizza. But I need my pizza fast, right? So I find that Domino's claims that they can deliver a pizza to me in exactly 15 minutes, right? But I'm a bit skeptical, right? And I want to verify this claim. So what I'm going to do is sample 40 pizza deliveries and record the delivery time for each, right? So in this sample of 40, right, I find that the mean delivery time is 20 minutes with a standard deviation of 2 minutes. And I want to use a significance level of 0.05 to verify Domino's claim. Now, this 0.05 here is this threshold I was mentioning, right? This threshold is what we use to determine if a p-value we're getting represents a significant difference or a not so significant difference. So for example, one, how we set up hypothesis testing is to determine what we call the null hypothesis versus the alternative hypothesis. So the null hypothesis is denoted by H naught. The null hypothesis is essentially the claim that, we're told, right? So in this case, Domino says that they can deliver a pizza to me in exactly 15 minutes. So mu equals 15. This is the claim that we're testing, right? This Domino's pizza claim, right? Domino's pizza says that the mean delivery time is 15 minutes. So I'm going to use that as my baseline. So that's kind of what the null hypothesis tells you. We will also have something called an alternative hypothesis, denoted by H sub A, right? And the alternative hypothesis is, what do I really want to verify, right? So if I'm a bit skeptical that Domino's can deliver their pizza to me in exactly 15 minutes, maybe I want to test if Domino's pizza delivery time is longer than 15 minutes, right? Because if Domino's takes, say, if it turns out that Domino's takes, say, 30 minutes to deliver a pizza, then that's not good, right? And in this case, technically, if I'm skeptical on the exactly 15 minutes, I would probably say that, okay, the mean pizza delivery time is not exactly 15 minutes. It could be somewhere below 15 or it could be somewhere above 15. But in the case of the real world, right, we are kind of concerned if the pizza delivery time is much longer, right? So the alternative hypothesis is going to be that mu is greater than 15. I know this question isn't the best worded question, but in this case, in the real world, right, we're more concerned if a pizza delivery time is longer than what we expect, right? So this is our alternative hypothesis. The mean is greater than 15, right? So what do? We have our sample, right? We need our sample as to build some evidence, right? So what is our sample information? Well, we know the sample mean is 20 minutes, right? We know the sample standard deviation is 2 minutes, and we know the sample size is 40, right? And we also know that the significance level denoted by alpha is 0.05, right? So in the case of this, right, we know that 40 is greater than or equal to 30, right? Because we're studying means. So by the CLT, right, the sampling distribution of the mean is approximately normal, right? Because 40 is bigger than 30 and it's a large enough sample, right? Okay, so now that we know that 40 is greater than or equal to 30, right? We know that we have this approximately normal assumption, right? So we can use the z distribution, right? So in the z distribution, right, what do we have? So the z-score is going to be the sample mean we get minus the mu over s sub x over root n. So the sample mean we are having is 20, right? And this mu right here will represent our null hypothesis value because we're assuming at first, initially, that the mean pizza delivery time is 15. So we're assuming that we have a distribution that's approximately normal, centered where the mean is 15, right? And the standard deviation is 2. So we're going to assume that, right? So that's why mu in this case will be 15, right? Because we want to compare against, we want to initially assume that, okay, Domino's can deliver the pizza to me in 15 minutes, right? And our sample mean we get is 20. So we want to find where does 20 lie in this distribution, right? So 20 is going to be right here, right? Somewhere, right? So that's why we have 20 minus 15 in the numerator. The sample standard deviation is going to be 2. And the sample size is 40, so we're going to have this. So our z-score that we're going to use is approximately, let me punch this into my calculator real quick. So 15.811. So so in this case, since our alternative hypothesis testing, if we're getting, the mean above 15, we actually have a one-sided or a one-tailed test, right? So we're having a one-tailed scenario, right? Because we only care about the alternative hypothesis as the mean greater than 15. We don't care about the mean not equaling 15, where we have to consider two possibilities. We only consider the case where the mean exceeds 15. So it's a one-tailed test, right? So what we want to do is we want to find the probability of getting a z-score that is more extreme than 15.811. This is equivalent to the interpretation I was mentioning earlier, where we want to find what's the chance of getting a sample mean that is more extreme than 20. And in this case, we want to see what's the chance of getting a sample mean that's above 20, because that would mean that we're getting more potentially significant results. So basically, this is equal to finding the probability of getting an x bar greater than or equal to 20. We're just converting it into a z probability. That way we can use our z table. So basically, what we're trying to do is we're finding this area here in green. And this point here is 0 because we're using the standard normal distribution. And it turns out, like, even if you try looking in a z-table, 15.811 is an extremely high z-score, right? And this probability is like very, very small. So like probably it's like less than like 0.0001, right? So our p-value is extremely small, right? It's much, much smaller than probably 0.001, right? But what was our significance level? 0.05 is the threshold, right? So if the p-value is extremely small, right? Like probably smaller than 0.0001, 0.0001 is less than 0.05. So it looks like the sample is significant, right? The sample mean we get is significant, right? In that our sample mean is statistically significant from the claim that Domino's is making of 15 minutes, right? So the p-value is less than 0.05, which is our threshold. So we can actually reject H naught, right? So what does this mean exactly, right? We have evidence in favor of the alternative hypothesis, and we don't really have much faith in Domino's claim that the mean pizza delivery time is 15 minutes. So we actually reject the null hypothesis in this case. All right, so we move on to example 2. So example 2, an organization reported that teenagers spent 4.5 hours per week on average on the phone. The organization thinks that currently the mean is higher. 15 randomly chosen teenagers were asked how many hours per week they spend on the phone. The sample mean was 4.75 hours with a sample standard deviation of 2. Conduct a hypothesis test with significance level of 0.1 and interpret the results. All right, so what's the null hypothesis? Well, we find that the mean time spent on the phone is 4.5 hours. The alternative hypothesis, the claim we're testing, is the mean is actually more than 4.5 hours. So what do we have here? We have our sample is 15. We have our sample mean is 4.75. We know that the sample standard deviation is, in this case, 2. And we know that our significance level is 0.1. So we know that the sample size of 15, right, is less than 30. So CLT doesn't work, right? So we can't assume that the sampling distribution in the mean is approximately normal, right? So we're going to use the t distribution, right? So when we use the t distribution, right, we need to get a t-score, right? So the t-score is going to be the sample mean minus the mu over s sub x over root n, right? Just like how we calculate the z-score, we're just using the t-score instead, right? Formula is exactly the same. So the sample mean is 4.75. The mean that we're testing on is 4.5 because we're assuming in this case that the mean time spent on the phone is 4.5 hours. We're assuming that to be true for the time being and then seeing if that sounds plausible, right? And then the standard deviation is 2 with a sample size of 15, right? So the t-score, I'm going to punch this into my calculator real quick. It's going to be this. It's going to be 0.484 approximately, right? So what we notice is that this alternative hypothesis is the mu is above 4.5, right? So we still have a one-tailed scenario, right? So we have this t distribution, right? And we're under the assumption that 4.5 is the mean, right? And our sample mean becomes 4.75. Since we care about one side, we want to find the probability of getting a sample mean that's above 4.75, right? Because that represents an observation more extreme than my sample, right? So I'm just trying to ask myself, what is the chance that, how surprised am I from observing a sample where the sample mean is 4.75 in a world where it's assumed that the mean amount of time spent on the phone is 4.5 hours? So that's what this green area can be also thought of. It's what's the chance that I'm surprised, basically, right? So this is equivalent to finding the probability of getting a t-score above 0.484, right? So what I'm going to do is pull up a t-table, right? And we're going to like take a look into the t-table. Oh, and one thing I forgot is the t-table, we need degrees of freedom, right? Degrees of freedom is 15 minus 1, which equals 14. So I'm going to go and, so what I'm going to do is, my t-score is 0.484, and the degrees of freedom is 14. So what I'm going to do is go to my t-table, degrees of freedom 14, and I'm going to look for where I'm going to look for where I have 0.484 or surpass it. Well, it looks like here when the degrees of freedom was 14, at 0.692, the tail probability, this probability here, which is the region we care about, is 0.692. So this probability of getting a t-score, right, above 0.484 is some number that is, bigger than 0.25. So my p-value, right, is, above 0.25, but the alpha is 0.1. So if my p-value is above 0.25, right, then my p-value must be above 0.1, right? So I actually fail to reject the null, right? So what does this mean to fail to reject H naught, right? Well, what this means is the sample mean of 4.75 in the context of a world where, the sample mean or the true mean is 4.5, this sample is not very surprising, right? So this is not a very surprising observation, right? In that the difference between 4.75 and 4.5 is not a very statistically significant difference, right? And it's just that my p-value is too high, right? We want our p-value to be small. That way we can say, okay, if the null hypothesis was the case, right, then I would be then my sample mean is somewhat far-fetched, right? But in this case, getting a sample mean of 4.75 in the context where 4.5 happens to be, say, the true mean, it's not a very far-fetched observation, right? So my p-value reflects that, right? So we actually fail to reject H naught, right? Now, in this case, this is failing to reject H naught is not the same as accepting the same. Let me repeat that. Failing to reject the null hypothesis is not the same as accepting the null hypothesis. We don't actually know if the null hypothesis is inherently true. What we can say is, do we have enough evidence to doubt the null hypothesis? And in this case, since we failed to reject the null hypothesis by getting a p-value that's above 0.1, we don't have enough evidence to doubt the null hypothesis. So what that might entail might be, me resampling and doing the test again, right? Or it might be the case that I might want to test a different claim, right? It honestly depends on your problem, right? But failing to reject H naught means that we don't have enough statistically significant evidence to doubt the null hypothesis. So this is just a brief review on hypothesis testing, but for means. Hopefully this video kind of gives you a good intuitive explanation on the p-value and also why we're doing the procedure the way we are to statistically verify a claim. So till then, tune in next time for when we talk about hypothesis testing for proportions. Have a good rest of your Saturday, and I'll catch you later.